Hi, good evening, Sudarshan. I'll just wait for a minute or two and then I'll start, okay?
Okay, sir.
Hi, tuning once again, and welcome to the week 7 of this problem solving session on this course, advanced topics, advanced power electronics and control. Right. So in this week, we will be covering problems on AC to AC converters, right? So this week probably you covered mostly about space vector modulation, the space vector PWM technique, which was an extension of what you were studying, right, in your DC to AC converters or your inverters. You did study about different types of PWM techniques, and in the end, you went through space vector modulation, right? So you get a lot of advantages with space vector modulation, obviously, as you might have learned. Okay, yeah. And then you started off with AC to AC converters. That is, first you studied about the regulators which you implement using conventional ACRs or thyristors. You learned about single phase and three phase AC regulators, right? And then you went into cycloconverters, in which again you learned about single phase and three phase cycloconverters. And finally, you studied matrix converters, right? So in matrix, you did study about different types of matrix converters and stuff. Okay. Fine, but mostly we'll be solving problems based on AC to AC regulators and cycloconverters. Okay, so that will be my point of focus today. Okay, so we will go ahead and start. But before we start, I would just like to discuss some fundamental points on your normal AC voltage regulators, because that's an easy topic in which you might be asked a lot of problems numerically. So I thought I'll just start off with that. Okay. Some basic stuff which is quite relatable to what you learned in your AC to DC converters or rectifiers, right? Using thyristors, because three phase and single phase AC regulators are also realized using thyristors or ACR, so you can easily relate both your full wave rectifier using thyristor and your AC regulators as well. They are quite similar in their operation. Okay, so let's start off with that. Um, okay. So let's consider the case of a single phase full wave AC voltage regulator. AC voltage regulator with an R load. Okay, single phase full wave AC voltage regulator with R load. So what's the circuit? It's a pretty simple circuit. As you might know, you have an AC source and then you have two ACRs, right? Connected in anti-parallel. You have two ACRs connected in anti-parallel, and then you have the resistor, right? Okay, so you know that this is going to be R and this is your VAC, and you have your resistors T1 and T2. Okay, your VAC is something like VM sine omega t. Okay, fine. So the idea is that let's say it has T1 has a triggering angle of let's say alpha 1, and let's say this is some beta 1. Okay, so then what will be the output voltage? Or let's say for now, for simplicity, we can assume alpha and beta to be same. Then in that case, what happens is something like this. So you have your input voltage, which is one cycle of your input voltage. Okay. So then what to expect to see in the output is something like this. Okay. And then you have, right. So this is something very that seems very familiar to you just because you studied it in rectifiers, right? In rectifiers, you got similar kind of waveforms. Okay, and you were able to derive all parameters such as the RMS value of your output voltage, then the current through each switch and stuff. So because this is very much relatable to that, I am telling you this. Okay, and this is a potential area wherein you might be asked problems like these. That is, find out the current through the switch, find out the peak current, RMS current through the switch, or what is the power delivered to the R load and stuff. Okay. So if you're good with this concept, it would help. Okay, so you know that this is 0, this is alpha, pi, and then you have your pi plus alpha, and then finally 2 pi. Right? So since we are dealing with an R load, what do you expect to see as your current, device current is something similar in wave shape to your output voltage, right? So this is your device current. Okay, so I naught. or not your device current, it's your load current or it's your I naught. Okay, so this is pretty much simple, right? You have a single phase full wave AC voltage regulator with an R load. Okay, and then we just drew the waveforms, which are quite logical so far. Okay, so you'll just try to derive what is the RMS value of your output voltage. Okay, so what's happening over here is you had an output voltage something like this, right? So this is your V naught, and you of course know this is your 0, alpha, pi, pi plus alpha, 2 pi. So as you can understand, right? So this is actually half wave symmetric. Half wave. Okay, so this is half wave symmetric. So you just need to consider the cycle between 0 to pi. Okay, so what will be your RMS value of output voltage? It is going to be something like VR, as I would denote it. By your basic definition, RMS is simply root mean square, right? So root over mean. So 1 by t integral, whatever is the 0 to t period, or we should call it capital T, right? And then f square of t dt. This is your basic definition of RMS, root mean square, right? Simple. So over here, if you just apply that, what you're going to end up is something like this. So your period is, since it is half wave symmetric, it is 1 by pi, right? And then you have your wave between alpha to pi, and it's following your input voltage, which is Vs, right? Vs. Vs is basically Vm sine omega t whole square d omega t in this case. Okay. So now it should be easy peasy for you. So Vm over root pi, if I might take it outside, and then I have a square root over here. Okay. So we have sine square omega t. So what is sine square omega t? Sine square omega t is basically 1 minus cos 2 omega t by 2. Right. So just apply that knowledge over here. So you will end up with 1 by 2 into 1 minus cos 2 omega t. Okay, and it is being integrated, right? D omega t. Okay, so your if you want to copy or something, I'll just give you a moment. Okay, so we were just deriving the RMS value of your output voltage for a single phase half wave rectifier. I mean, single phase full wave AC voltage regulator. Okay, so this is your VRMS, right? So once you have your VRMS, so what we can further simplify is something like 1 by root pi, right? And then integral alpha to pi, right? And then, so I will take the root 2 as common over here. And then we had integral 1 minus cos 2 omega t, right? So it is going to be something like integral d omega t is just omega t. So it's going to be pi minus alpha over here plus integral cos 2 omega t, right? So integral cos 2 omega t, as you all know, is sine 2 omega t by 2. Therefore, it's not a plus, it's a minus. So it is going to be minus sine 2 omega t by 2 between alpha to pi d omega t. Okay, and it is all in square root, right? So it is going to be 1 by root 2 pi, or pardon me, Vm by root 2 pi, Vm by root 2 pi into root over pi minus alpha, right? So and then you have sine 2 pi is anyway is going to be 0. So pi minus alpha plus sine 2 alpha by 2. Okay, so this is your VRMS, right? So your VRMS is Vm by root 2 pi into root over pi minus alpha by 2. If you remember right, This is actually very similar or the same as VRMS of a single phase full wave rectifier. So you see the formulae are same. You just need to connect the dots and that's it, right? So your VRMS of your single phase full wave AC voltage regulator, this is the same expression as what you got for a single phase full wave rectifier. Okay, even though it's a regular, it's a AC to AC converter, you are seeing that the RMS value is same. Why? Why is it so? Because from the wave shape itself, you can understand, right? It is half wave symmetric, right? It was same for single phase full wave rectifier. You would have got something like this. For a single phase full wave rectifier, you would have got something like this. Just that over here, this period is inverted, right? This period is getting inverted, correct? So can someone tell me till this point if you're here? It is very similar to a single phase full wave rectifier. Why? Because your wave shapes are almost similar, just that it's AC and over there in single phase full wave rectifier, you saw it was a DC. Okay. Now what you are doing here, you are finding the root mean square, right? Root mean square, RMS, right? So what is root mean square? First, you are squaring the waveform. When you square this waveform, when you square a negative waveform, right? So a square of a negative becomes positive, correct? So that is why if you square it, it is going to become the same waveform as the square of your full wave rectifier, and then you are taking the root. Got it? So your RMS is same. Did you guys understand why your RMS is same? Can someone reply? Or you want me to repeat this point?
Understood.
Okay, thanks. Okay, so as I was telling, since this is an RMS quantity, it is same irrespective of whether it's your full wave rectifier or it's a full wave AC voltage regulator. The reason being that in RMS, you take the mean, I mean, you take the square first, then you take the mean and then do RMS. Okay, so first you square it. That is, you're doing kind of a mod operation. Okay, because you're doing a mod operation, what happens is your waveform becomes inverted or your waveform becomes positive. Okay, because it's a mod. And then you're taking the mean of that waveform and then you're taking a root of that. So obviously you understand that the values are going to be same. Okay. So any question similar to what you are seeing for what you saw for a full wave rectifier, it is also applicable for in this case. Okay, and you can find it in the very same manner that what you did for full wave rectifier. Okay. Okay. Okay, fine. So then we will go move on to the next parameter. So this was about your RMS, right? So what about your power factor? We need to talk about your power factor since we are dealing with AC quantities over here. So what you see in this waveform is something like, see, if I might redraw the voltage and current, right? So what happens to your input is something like this, okay? And your output is going to be something like, right? So this is your, okay, I should not be drawing this. So your output is, okay, in case you have an R load, your current is also going to be the same way. Okay, so this is your current. Sorry for that, I lost contact in the middle. Thanks for hanging around. Okay, so I think we were here, right? Like we were discussing about the similarity of your RMS voltage with respect to rectifiers. Okay, so similarity of your AC voltage regulators with respect to rectifier, right? So you understand that the reason it is similar is because you have your root mean square over here. First, you are squaring it, right? So you are squaring the voltage. And then what you are doing is, since you are squaring the voltage wave shape becomes same as your rectifier case, right? So you are squaring it and then taking the mean and then doing a root. Okay, that's your root mean square. Since you are squaring it, you are taking kind of a mod operation, right? So it's a mod operation. RMS is basically a mod operation and then a root of it. Okay, mean of your mod and then the root. Okay, that is why you see the similarity with respect to your rectifiers, correct? So not only your RMS voltage, so this was about your RMS voltage. You will see going forward that probably I lost you guys over here. You will see going forward that your distortion factor, THD, that is your total harmonic distortion and power factor, right? So all of these are actually quite similar to your rectifier case. So whatever you studied over there for rectifiers, that is whatever formula you went over there, all of them are applicable for your AC voltage regulators as well. Okay. So one thing I wanted to mention was, I'll just explain the. So was this concept told to you or not, about the source current? Can you guys tell me? Hi Sudarshan, can you tell me if I told you about the source current of your um, AC voltage regulator or not, or at that point itself I lost contact with you?
I don't think you talked about.
Okay, okay, thanks, Abhishek. Okay, so what I wanted to tell was, okay, if you consider your basic full wave rectifier, I mean full wave AC voltage regulator, so what you have is something like this, correct? So this is your circuit. Okay, so V, you have an R and then T1. So the point is, if you draw the waveforms, right? So this black is your input voltage, but what happens to your output voltage is something like this, correct? And similarly, since it's an R load that we have considered so far, your current is also going to be something like this. This is your output current. Okay, so this is your V naught and I naught. So what will be IS, right? So your source current. Your source current will flow only when these two thyristors, either of these two thyristors are on. Either T1 or T2 need to be on. Therefore, you will see that your output current waveform is also going to be something like, I mean, your input current waveform is also going to be something like this. Okay, so this is your Vs and Is. So you understand that your input current is non-sinusoidal, correct? Which means that you are going to have a non-zero THD. Okay, you're going to have a non-zero THD and you're going to have some distortion factor which is less than 1. Okay, and a power factor as well. So what will be that power factor? So basically these components will tell you how non-sinusoidal the wave shape is, right? If it is 1, it means that it's perfectly sinusoidal. But over here, the power factor is actually the same as what we saw for your rectifier case. So the power factor is going to be V naught RMS divided by V source RMS. Mind you, this is applicable only when you have an R load and your current wave shape is similar. Only because your current wave shape is similar, I'm telling this, right? Okay. And like this, all the components, I mean, all the terms are applicable. They are the same as what you saw for your full wave rectifier case. Okay. And then what will be the power delivered to the load? This is where I realized that I lost contact with you guys. Anyway, so the power delivered to the load will be simply V naught RMS square over R. Okay, so we just derived what was V naught RMS. Okay, just square it and divide it by R. You are going to get what's your power delivered to the load. Okay. Okay, so one point is, okay, this is the power delivered to the load. Now you understand that the power over here, this is the average power, right? So this is the average power delivered, or let me tell it's the useful power delivered to the load, right? It is a useful power delivered to the load, which can actually be used for heating purposes because your RMS is the quantity which is responsible for heat production, correct? Okay. Now the point is, if someone asks you what is the peak power delivered to the load, peak power delivered to the load. How do you find the peak power delivered to the load? Power is still going to be power as you saw was V naught RMS square over R. Okay. So what you can actually do is for a peak power, right? So when is your V naught RMS maximum? Right? Over here, V naught RMS is maximum at alpha equal to 0, right? So what will be at alpha equal to 0? At alpha equal to 0, your V RMS is going to be Vm by root 2, correct? And this is the maximum value of RMS voltage that you can get. Okay, at alpha equal to 0, it means that it is simply the converter is not functioning at all, right? The AC is simply passing through. It's in pass-through mode. The converter is in pass-through mode, right? So at alpha equal to 0, your VRMS is going to be maximum. Okay. So you can understand that the peak power delivered to the load occurs at alpha equal to 0 degrees. Okay. And the power is going to be something like VRMS square over R. That is your Vm by root 2 the whole square over R. Okay, that is going to be Vm square over 2R. Okay, so this is the peak power delivered to the load. Got it? Okay, so if this is fine, please do let me know if you have any doubts regarding this or else at any point of time. Okay, if this is fine, I will move on to the next case. That is, let's say I have an RL load. Okay. So let me redraw the circuit, obviously. So you have something like. Okay, so you have an RL load. So VS, RL, T1, T2. So I'm taking a lot of time with these regulators because this is an area where you will be asked a lot of questions. Okay. So once I make this clear, I will go to questions. We will be dealing with questions on cycloconverters as well. But this is a simple area where you can easily score marks as well if you kind of correlate with your full wave rectifier. Okay. So if you consider an RL load, let me just draw the waveforms. In that case, what happens is you of course have the input voltage, right? So what will happen to your output voltage and output current? Okay, let's draw the output voltage alone. So what you will be seeing is it will of course start conducting at alpha. Okay, so it will conduct till this point and then it will be something like this, correct? So this is your alpha. I mean, this is your V naught. Okay, this is your V naught. But what about your current? So the current value over here depends on what is the value of R and L, particularly L. Okay. So what you understand that an inductor opposes change in current, right? So it doesn't like discontinuous current. An inductor doesn't like currents like this in spikes. An inductor likes a current something like this, continuous current, like similar to what you saw in a buck converter. Okay. So as your inductor increases its value, or as the value of the inductor increases, you will see that the current becomes more and more smoother. Okay. Basically, L is used for smoothing the current. That is why L is used as filters in a lot of applications. Okay. So inductors used for filtering purposes, just to make the current smooth, continuous. Okay. So L doesn't like spikes in current. So the point is, depending on the value of L, your um, current wave shape will vary. Ideally, what you would expect is, because of this L, you're going to get a lag, obviously, right? So you understand that your current will obviously start from zero over here, and it may not necessarily end at this point itself, right? So what you would expect to see is something like it may end over here, right? So it may end over here. Okay. So your output voltage is going to be something like this, correct? And this, right? So this is how your output voltage would be. It's the same as what you saw for full wave rectifiers. Okay, so your inductor current may end over here. And then again it will start from here. I'm sorry. Again it will start from here and then end over here and so on. Okay. So this lag, this phase shift, or if I call this point as beta, right? And this is pi plus alpha, pi. So this is pi, this is beta, and this is pi plus alpha. So the point is the value of beta is fixed by your L. Okay. So your beta will be pushed more and more. Your beta will be higher if your L is higher. Simple, right? Your beta will be higher if your L is higher. Okay. And what is this value of phase shift? This phase shift, if I call it 5, right? This phase shift, okay, let me not call it 5. Let me call this as just phase shift itself, because 5 will be asked in a question. Okay. So this phase shift, as you can understand, depends on L. If your L is more and more, this particular period is going to be more and more. Okay. Now there comes a point when your L is so large, that beta equals pi plus alpha. Okay, there will come a point, or there will come a value of L when beta equal to pi plus alpha. So from that moment on, what will happen is your inductor current will be continuous, right? So your inductor current is going to be something like, okay. So this is what will happen if your L is too large. Okay. So who fixes this phase shift, right? So
Sir, output current should have been sinusoidal like AC, right? This is DC.
Yeah, yes. I got it. Thanks for correcting. I drew it from the perspective of rectifiers and I was just stuck up there. Thanks for reminding. Okay. So as you rightly pointed out, your current is going to be something like, right? It will become continuous at some point of time. So that value of beta is your, I mean, you may not call it extinction angle from now on, because beta has become equal to pi plus alpha. Okay. So it's just continuous conduction. Okay. So what dictates it? Is there a relation which gives me what value of L will make this happen, right? So what value of L will make this happen, right? Is there some relation with the firing angle? If I can relate alpha with your phi, right? What is your phi? Phi is basically your tan inverse omega by L. I mean, tan inverse omega L by R. Okay. Where R and L are your load. So phi is tan inverse omega L over R. If I can relate this angle, this particular load angle, as we might call it, so this phi is your load angle, right? If I can relate my load angle and firing angle, I can determine at what point or what value of firing angle my converter is going to be continuous. you can understand that if the converter is continuous, right? If the converter is continuous or if this is happening continuously, then you're no longer having a control, right? Your control is lost because your current has become continuous and your voltage is going to be something like, your voltage will be something like from here till this point, correct? And then again it will continue and then it will reach here and then it will just continue, right? Basically, you will be getting a sine wave. That's what I want to emphasize, right? So you'll be getting a sine wave and this will just go on. That means that your converter has become uncontrollable, right? So the point is, if L is too large, right? Then what happens is your beta tries to go more than your pi plus alpha. In that case, your V naught, I naught are continuous. Okay. And they are uncontrollable. Okay. So the idea is, okay, at what point does the converter become continuous? At what point does the converter become uncontrollable? Okay. Turns out that if your firing angle, right? Let me write with a different color over here. If your firing angle alpha, right? If your firing angle is less than phi, if it is less than phi, then your converter is controllable. Okay, and it is discontinuous. But if your alpha is more than phi or your firing angle, you're going to be continuous and uncontrollable. Got it? So there is a relation between, obviously you can understand, right? I'm not going to the derivation part, right? But you can understand that there is a relation between your firing angle and your load angle. Turns out that if your firing angle is very less than your phi, then the converter is controllable and discontinuous. And if it is more, it's continuous and uncontrollable. Or, yeah, I think I have told it the other way around. Sorry. You understand, right? Okay. Okay. So, yeah, correct. So if your firing angle is, obviously, if it is closer and closer to your pi, right? Let me draw it over here itself. So you saw that. Okay. So this is one case. The other case may be something like it started conducting here itself. Right? So if your alpha is lesser and lesser, then it becomes more and more closer to pi. Okay, or the difference between pi minus alpha goes on decreasing. So there is a greater chance that your beta becomes equal to pi plus alpha. In that case, if your alpha is very less, if alpha is very less, there's a greater chance that your beta will inch closer to pi plus alpha. So there's a greater chance that your converter may go into discontinuous mode. I mean, continuous or uncontrollable mode. Okay, so the idea is your alpha should be, yeah, your alpha should be more than phi. Okay, if your alpha, the firing angle should be more than phi. I mean, means that this point should be more towards the right hand side so that your converter is more controllable and you get a discontinuous wave chip at the output. Okay, so you can always relate your load with the firing angle and decide a value of firing angle accordingly based on the considerations. Okay, so based on that, I will just give you guys a problem before we go ahead. Okay. Okay. So the problem is, let me call this problem number 1. Okay. So the problem is you have a load of 50 ohms. Okay. And you also have an inductive load of 50 ohms. Okay. Excel, as I have written, it's an inductive load. I have an inductive load of 50 ohms and an R of 50 ohms as well. Okay. At what value of firing angle At what value of firing angle V naught becomes uncontrollable? Right? So this is the question. At what value of firing angle V naught becomes uncontrollable? Okay. So ये 45 and um, okay, so these are the four options. So you remember, okay, so of course we have, you know that obviously the options cannot be B or D, right? Because I told you that for alpha less than phi, it becomes continuous and uncontrollable. That means that the uncontrollable range is between 0 to P, right? This is your uncontrollable range, correct? Your uncontrollable range is between 0 to 5. Okay, so obviously your lower limit is 0. So this is one hack to find out what is the uncontrollable range. That is, obviously you cannot have options as B or D. It is either A or it is either C. Okay, so this is a hack. In case C had something like this, maybe 60 to 100 or something like this, then you obviously know that A is the answer or vice versa. Okay, so your lower limit needs to be 0, right? So let me just state it over here. If alpha less than phi, uncontrollable. If alpha more than phi, it is controllable. Okay. Okay. So as I told you, XL and R both are 50, right? So R is 50 ohms and XL is also 50 ohms. Okay. So what is your phi? Phi is tan inverse omega L over R. That is tan inverse XL over R, right? So tan inverse 50 over 50 is 1. So what is tan inverse 1? 45 degrees. So the answer is if your alpha less than 45 degrees, if your alpha is less than 45 degrees, uncontrollable. Okay. Therefore, what's the correct answer? The answer is this. Okay. If your alpha is less than 45 degrees, your converter is going to be uncontrollable. Got it? So till this point, we are actually done with today's theoretical part. So till this point, do you guys have any doubts? If you have any doubts, please do go ahead and ask. Yeah, so Divakar, just a second, I'll just check the chat. Yeah, so Divakar, phi is actually your load angle. Okay, I was mentioning, right? Phi is your load angle. So let me restate that for your convenience once more. Okay. So the point is we were discussing about single phase AC voltage regulators having an RL load. Okay. So if you have an RL load, the load will have a load angle. Okay, so this is your load angle. Phi is actually tan inverse omega L by R. You can understand, right? It's just basic networks. So for this RL load, this RL will obviously give a lagging power factor, correct? It's going to have some angle or lagging angle. So what is that angle? So that is actually phi. Phi is basically tan inverse omega L over R. Okay, or tan inverse XL over R. It's your inductive impedance to your resistance of the circuit. Okay. Now the point is at what value of phi, right? At what value of alpha, your beta and pi plus alpha are going to coincide. That was what we were discussing, correct? So you want me to um, do you want me to, if you want me to explain, okay, let me explain over here. Um, so we told that your output voltage in a single phase will be AC regulator is going to be something like this, right? With an R load. With RL load, what will happen is you're going to get something like, and then you have a negative region over here. Okay. So you have something like, you have a positive region. So what will happen is, right? So you have pi over here, and then beta over here, and then pi plus alpha over here. Okay. So this beta will go on increasing if your L increases, load increases, the L of your load increases. At some point of time, what might happen is you will get something like, it is beta is so high that it will coincide with pi plus alpha, right? So you will get something like this. So it will just go on. It will just be a sine wave, right? So you can understand it's going to be just a sine wave. Okay. And your current, right? Your current would be something like, initially it would be something like this. Okay. And then it would be something like this. Now, if your beta goes on increasing, what would happen to the current is your current would be something like this, right? So again, it would be sinusoidal. Okay, of course, with a lag phase shift. Okay, this is something you don't want, right? Your current is also uncontrollable right now, and your voltage is also uncontrollable. Correct? Output voltage and output current both are uncontrollable. And this phase shift lag is purely defined only due to your phi or your load angle, tan inverse omega L by R. You don't want that. So I wanted to find out at what value of firing angle your converter becomes uncontrollable. Okay, so that is what I told you, that if your alpha is less than phi or the lag angle, if your alpha is less than phi, your converter is uncontrollable. And if your alpha is more than phi, if your alpha is too high as shown over here, right? If your alpha is too high, then pi plus alpha is more than beta. Pi plus alpha is more than beta. Okay, if your pi plus alpha is more than beta, then your converter is controllable. Okay, so that is what I was telling you. So your phi is your load angle. Okay. Okay. So, fine. So, please give me just a break of 2 minutes. I'll just have some water. I guess. Okay. So if this is fine till this point, we can go ahead with the rest of the problem. So we have discussed enough theory, so we will go into a bit of problem solving. Okay. Fine. A single phase half bridge inverter has RLC load. Okay. The DC input voltage Vs is equal to 230 volts and the output frequency is 50 hertz. The expression for the load voltage up to the fifth harmonic will be given by what? Okay. So this is an inverter problem. Yes. Um, just excuse me for a second. Yeah, sorry for that. Yeah, so the question is a single phase half bridge inverter has RLC load. The DC input voltage Vs is equal to 230 volt and the output frequency is 50 hertz. The expression for the load voltage up to the fifth harmonic will be dash. Okay, so the question from this from the given options itself, you can actually try to eliminate options that are not relevant for you guys. Okay, so the point is, as you can understand, you only have odd harmonics, right? Even harmonics eventually get cancelled out in a sine wave, correct? So obviously the option is not going to be C. Okay, so it is either this or this. Okay. So the next hack is, okay, what happens in harmonics? Your frequency is going to be multiplied, right? Omega n is going to be n times your omega fundamental. Okay, that is one. Omega n or the nth harmonic frequency is going to be n times your fundamental frequency. In this case, it's 50 hertz, right? And the other one is going to be your amplitude, right? Your amplitude an is going to be whatever is your fundamental amplitude AF, if I call it fundamental, divided by n, right? So it's going to be, its magnitude is going to come down. Okay. So if you're having 1 unit of magnitude in the fundamental, in the third harmonic, it's going to become 1/3. In the fifth, it's going to become 1/5, and so on, right? So as your harmonic order increases, your amplitude actually goes on decreasing. Okay. So this is the hack. So from the given option itself, you try to eliminate. See, in A, uh, you have second harmonic, fourth harmonic. Okay. So obviously, this cannot be the answer. So the answer is either B or D. Okay. So you can understand that over here, it is 314, 3 into 314, 5 into 314. That is omega n, right? Omega n is 1, 3, and 5. Okay. 314 is your fundamental. Okay. If you convert kind of 50 hertz, right? So 50 hertz in omega, what is 50 hertz? Omega is 2 pi f, right? So 2 pi into 50. So 100 pi or 100 into 3.14. So 314 radians per second. Okay. So 314 radians per second. Okay. So the point is, this is your frequency. But what about your amplitude? Amplitude should be scaling down by n, right? So 146, then it should be 146 by 3 and then 146 over 5. If this is satisfied, then it's the answer, right? So 146 you have over here. So you do 146 over 3, it's going to be 48.8. Why? Because 150 over 3 is 50, right? So this is correct. And again, 146 over 5 is going to be 29. 150 over 5 is 30, right? So obviously B is the correct answer. Okay, so this is how you should eliminate instead of just, if you solve it, of course, I have the solution. Okay, so in a single phase average inverter, you understand that your VA naught is going to be something like this, right? So you have square wave. Okay, so if I might go back, right? So in the this is the circuit of a single phase average inverter. Okay, so if you draw the circuit, what you know is eventually when your S1 is on, this is going to be something like this. And if your S2 is on, you're going to get something like this. This is a loop. Okay, if you split, this is VD by 2, VD by 2. Okay, so it's your VD by 2 and this is your VD by 2. So what happens is if your S1 is on, so then um, you're going to get a plus VDC by 2, right, across VA naught. And if your S2 is on, you're going to get minus VA naught by 2. You understand that it's going to be a square wave, right? It's a square wave. Why? Because you're having a discrete voltage of VDC by 2. And if your load over here is an R load, resistive load, your current is also going to be a square wave. Okay. As you can understand, the square wave is composed of infinite harmonics. Ideally, this is composed of infinite harmonics. Correct? Okay, it has infinite harmonics in it. Therefore, so what we do is simply if we apply Fourier wave, right? What happens? You get sigma 2 VDC by n pi sin n omega t. Why is it like that? For a square wave, it is basically 4 times the voltage divided by n pi sin n omega t. Okay, but over here V itself is VDC by 2. Okay, that is why I have written 2 VDC by n pi, because V itself is VDC by 2, right? The amplitude itself is only VDC by 2. Okay, so it is 2 VDC by n pi sin omega t for odd n. Okay, so you substitute over here, you will be getting whatever was the options given there. So 2 VDC by n pi, right? So 2 VDC by pi is basically 146.42 because your VDC was given as 230 volt, right? So so it is 2 into 230 by pi, you get this. Okay, so then this is your fundamental, and your 1/3 is going to be 146 by 3, and then 146 over 5 is going to be your fifth harmonic. Okay, so this is the actual way to do it, but if you guys want to do it faster, you can use the hack which I told you. That is just, you know, that only odd harmonics are going to be there, right? Therefore, option C is definitely not the answer. Option A has both odd and even, so option A is also not the answer. And so therefore it can be either B or D, right? So why did I tell B is correct? Because not only are the frequencies matching, even the amplitudes, if you see, right, it is 1 by 3 and this is 1 by 5. Only because of that, I told B is the option. Okay, but the correct way would be to do like this. Okay, just using the Fourier series. Okay, fine. So the next problem is in a voltage source inverter, both voltage and current depend on load impedance. Only voltage depends on the load impedance. Only current depends on load impedance. None of the above. Okay. So try to understand. So what depends on load impedance? If you tell that something is depending on something, right? It means that it cannot be a constant source of anything, right? For example, if you tell 5-volt battery, right? If you tell 5-volt battery, it means that the battery essentially has to remain at 5 volt irrespective of the load, whether you open circuit it, right? Or you connect a 100 ohm resistor, you connect a 20K resistor, irrespective of what load you connect, the battery is a 5-volt battery, right? Then you tell that it is a source, voltage source. Only then you quantify or you qualify the battery as a voltage source. So you understand that means that the battery voltage is independent of your load, right? You assume that the battery voltage is independent of the load. It is maintaining 5 volt irrespective of whatever be the load, whether it's open circuit or 5K or 20K or 100 ohm or whatever it is. Similarly, from the name itself, you can understand. If you are aware of the nomenclature, you can solve this. if it's a voltage source inverter, you understand that voltage is fixed, right? Voltage is independent of the load. Okay. Therefore, only current depends on the load impedance. Got it? Voltage is independent. Current, of course, depends on the load impedance. Why? If you take the voltage source inverter, if you take the voltage source inverter, the current I naught can be something like this. If the current, if the load is a pure resistor, right? Then your current is going to be a square wave. Okay. And if your load is an inductor, it is going to be it's going to be a triangular wave, right? And something like that. And if you have kind of an R and L, you are going to be something like some kind of RL charging. Okay. And if you have RLC in resonance, if you have some kind of resonance, you may get something like even a sinusoidal waveform. So the point is, your current is dependent on the load, right? Based on the load, your current wave shape changes, but your wave shape of the voltage remains constant, independent of the load. Okay. That is why for voltage source inverter, only current depends on the load impedance. Okay. Fine. Okay, so cycloconverter is which type of converter? One stage power converter, one stage voltage, one stage frequency, or one stage current converter. So cycloconverter is basically what? It's an AC to AC converter, right? So obviously you understand that if it's an AC to AC converter, any converter will never change the power. Okay, the idea for every converter is that power remains constant. Pin is equal to P out, irrespective of whether it's your DC-DC converter, non-isolated or isolated, AC-DC, DC-AC, AC-AC, your power will never change. Therefore, this is obviously not the answer. So either it's a voltage converter, frequency converter, or current converter. Okay. The idea is, since it's an AC to AC converter, we tell that, okay, it is changing the frequency, right? That is, for example, if you have one pulse at the input, you may get multiple sinusoids at the output. That's the idea of cycloconverter. Therefore, the answer is one stage frequency, right? It's changing the frequency from 20 hertz, 50 hertz to maybe 200 hertz or something like that. It depends on the number of pulses. Okay. Yeah, so that's what is written over here. You have one phase to three phase conversion, but there is a difference in frequency Fi and F naught. You have an input frequency and an output frequency as well. Okay. Okay. So in three-phase cycloconverters, the reduction factor is what? So it is a basic definition. You might know that. So the reduction factor is basically output frequency by input frequency. Okay. So the answer is B. The reduction factor is given by output frequency over input frequency. Okay. A single phase bridge type cycloconverter has input voltage of 230 volt. As I have told it in earlier sessions as well, if they just give something like this, 230 volt, 60 hertz, it means that it's a RMS quantity. Okay. A single phase bridge type cycloconverter has input voltage of 230 volt, 60 hertz, and a load of R equal to 10 ohms. Okay. So output frequency is 1/3 of the input frequency. Okay. So for a firing angle delay of 30 degrees, calculate the RMS current of each converter. Yeah, I think it is the RMS current of each switch. Okay. So what? So in these kind of problems, it's better to draw the circuit and analyze it. Okay. So what happens in a cycloconverter? You have something like this, right? So this is nothing but a full bridge. Don't just get too confused. It's nothing but a full bridge, and again a full bridge in anti-parallel, and then you have the load in between. Okay, this is your cycloconverter, conventional cycloconverter. Okay. So this is what you expect to see, right? So you're going to see something like this. When your P converter is on, you're going to see some kind of rectification over here during this period. And when your N converter is on, you're again going to see a rectification during this period, right? Or during the other period, right? So the entire period is your 60 hertz, right? And within that, you are turning on and turning off multiple times, correct? Okay. So the question is, output frequency is 1/3 of input frequency. That is why the wave shape is something like this. The output frequency is 1/3 of the input frequency, right? For a firing angle delay of 30°, calculate the RMS current. Okay, so alpha is also given. Okay, in that case, just compute your V naught. Okay, if you compute your V naught RMS, right? So it's your V naught RMS, right? So just compute your V naught, and since it's a resistive load is what they have given, I naught is simply V naught RMS over R. Therefore, your individual converter current is going to be I naught over √2. So this is very similar to what we saw for full wave rectifier. Therefore, I'm not explaining how these formula came. I think I spent quite an amount of time deriving this particular formula itself. Okay, Vm by root pi into root of pi minus alpha plus into alpha by 2. Okay, so it is very similar to what we saw for full wave rectifiers. Just use the formula for the RMS voltage and then find out what is I naught. Once you find out what is I naught, then the question is calculate the RMS current of each converter. Okay, right? So you understand that what is your RMS? If you know the full current, okay, so your RMS of your one converter, right? If I call it P or N, whatever it may be, IRMS of one converter is IRMS total, IRMS P into root over T on by T. Okay, that is the idea. So IRMS of one converter. So this is for one converter. So IRMS of one converter is IRMS total, right? So IRMS total into root over T on by T. That is, so IRMS total is what? V naught over R, 22.66 into root over T on by T. So each converter is on for half the time period, right? So P converter is on for half and N converter is on for the other half. So it is basically 1 by 2, root over 1 by 2. Okay, and that will give you this. Got it? So your converter RMS current, let me write converter RMS current, RMS converter is equal to your total RMS current, I total RMS into root over T on by T. Okay. Fine. Okay. Okay. So this was just a calculation of the RMS. So the RMS correct answer is, they have given you everything alpha, R, and then V. So I just applied the formula for V naught and then computed what is the converter RMS current. Converter RMS current is total RMS current into root over T on by T. For how much time the converter is conducting out of the total period. Okay. Into root means square, right? That's why it's root over T on by T and you end up with this. So I'll just pause for a moment here so that you guys, if you want to calculate or compute it, you can just do it. Okay. Okay. So I will move on to the next question. It is very similar to the previous question, same question only. A single phase bridge type cycloconverter has input voltage of 230 volt, 50 hertz, and a load of R equal to 10 ohms. Output frequency is 1/3 of the input frequency. Same question. For a firing angle of 30 degrees, calculate the input power factor of the cycloconverter. It's the input power factor. Okay. So what did we see earlier? Input power factor is basically V naught RMS over Vs RMS for a AC voltage regulator, right? It's for a AC voltage regulator. Over here, they have asked for a cycloconverter. Okay. Okay. So again, you have the single phase cycloconverter, and these are the characteristic waveforms, which I believe you guys are very well aware about. Okay. So what is power factor over here? You understand that over here, it's a little bit different, right? Your Vs may be somewhere around 60 hertz, right? But you see that the output is having around 20 hertz, correct? So it is not 60 hertz, it's going to be 20 hertz. So this was 60 hertz, but what you are seeing is basically 20 hertz cycle. Okay. So you can't just directly use V naught RMS over Vs RMS. This is wrong. Okay. So you need to go by the normal definition of power factor. That is, what is power? Power is basically V I cos phi. VRMS, IRMS cos phi for a single phase case. So you can find out what is phi from this, right? If you know the power, so P by VRMS into IRMS should give you what is your phi. That is what we have done over here, correct? So the power factor is P naught by Vs into Is. Okay, correct. So idea is first you compute what is your um, unknown values. Okay. For example, over here, you don't know what is your IS, correct? So you know what is your R. This is known. And what is your VS? This is also known. Sorry. Okay. So your R is known, VS is known, and we just found out what should be V naught. Okay. So V naught is also known, right? If your V naught is known, I naught is also known, right? From the previous question, we know what is V naught RMS, we know what is I naught RMS. Okay. If I know both of these, since it is only an R load, I can find out what is a power. The power is basically V naught square over R, V naught RMS square over R. This formula is valid only when your load is purely resistive. Okay, cos phi is going to be 1. Okay, in this case also cos phi is 1. You note that only when cos phi is 1, this V naught RMS over Vs RMS is applicable. Okay, so this is what I wanted to tell. So when you tell that the power factor, as we saw earlier itself, is V naught RMS or Vs RMS. Okay, so this is applicable only when cos phi is 1. Okay, in your load power factor is 1. Only when, okay, let me clarify it. Only when load power factor is 1, overall power factor is going to be V naught RMS over Vs RMS. Okay, so that is what we have done over here as well. So we know what is V naught RMS from the previous question, and we know what is Vs RMS. Vs RMS is basically 230 volts, right? 230 volt was given. Okay, and what was V naught RMS? V naught RMS was 226.66 volt. Okay, so just substitute that. So 226.66. Okay, so just substitute it. You will be getting what is the power factor. Okay, so understand this particular formula V naught RMS or Vs RMS is applicable only when load power factor is 1. Okay, fine. A single phase voltage controller has input of 230 volt and a load of 15 ohm resistive. So R is given, again V RMS is given. For 6 cycles on and 4 cycles off, determine the RMS output voltage. So as I told earlier, basic definition of RMS is RMS, if you want to find out of something, then it is the RMS total into root over T on by T, right? So just intuitively you can find out it's going to be 230 into root over what is T on? 6 cycles, right? And what is your T? 6 plus 4. Okay, so it is basically 230 into root over 6 by 10. Okay, the answer should be somewhere here. You guys can calculate. I will also just compute. Okay. It is where's my calculator? If you guys find out earlier, you can tell me. So root over 0.6. So it should be 178.16 volt. So the answer is D. Okay, basic. You need not know cycloconverters for this. Just apply your basics and you will get the answer. So it's the total RMS into root of T on by T, right? So they have given 6 cycles on, 4 cycles off. Okay, so just apply it, you'll get the answer. Or you can go the conventional way, just draw it, right? And then draw the waveforms for your own convenience. 6 cycles on it is, right? So 0 to 6 out of the 16 pi and 4 cycles off. Okay, so that is what we are using. Vs into root over n by n plus m. Okay. Okay. Till this point, if you guys have any doubts, you can go ahead and ask. Okay. You guys have any doubts so far? Or if you want me to repeat anything or in any of the questions so far covered, you can ask, or I'll just pause for 2 minutes over here. You can just type in the chat box as well if you want. I'll just pause for 2 minutes here. Okay, so then we can continue. You guys don't have any more doubts.
So, what would be the input current frequency in cycloconverter?
Sorry, what would be the
Frequency of input current in cycloconverter, would it be same as the frequency of output current or
okay?
frequency of input voltage?
Uh, so okay, so from this, can you tell me what would be the frequency of input current? You see what is Vs and you see what is V naught.
This is not
V naught and I
cycloconverter.
naught. Sorry. Yeah. You are asking about cycloconverter. Okay.
Yes.
Correct.
Look,
Okay. So okay, fine. Got it. You are asking about CI. Got it. Okay. So the point is, you understand current can flow only when either of these two converters are on, correct? Either your P converter should be on or your N converter should be on. Okay. For simplicity, we will assume that it's just an R load. Okay. So then what happens? Your uh, output current is also going to be following your output voltage, right? It will be something like this. Is your okay. So this is how your output current is going to look like. So how so you just trace this current back to the from the source and you will get the answer. Okay, so let me just get rid of this. Okay, just a second. Okay, so over here the output current is going to be something like this. Okay. So this is how your current is going to flow. So if you take this particular section, right? So what would happen? It's going to flow something like this. So it is going to flow through this. Okay. So over here you apply KCL. So what is IS? IS is basically IP plus IN. Okay. So now you see what is the frequency of IP? Can you tell me what's the frequency of IP? What will be the frequency of IP? So when will IP flow? Abhishek, can you tell me?
When will IP flow? So for the first 3 cycles, I think
Correct. So
IP
for
will
the
be.
first, so your IP is going to be 0 during this period, and for the first 3 cycles, the current is going to flow. So how the current will be? Will it
If the
be
first
having the
cycle,
tell.
yeah, positive in the first 0 to pi, then it should be negative in pi to 2 pi input current.
Correct. Okay. So okay, so I should not be drawing the full cycle. Probably something like this. So it will be like this and then like this. Correct.
Yep.
Correct. And then you have something like this. Okay. So oh, I'm sorry. If I draw the same for the other one, this is the other converter in converter. Okay, you're going to get something like this. And if you kind of add it up, you're going to get your input, correct?
Yeah.
So you tell me what is the frequency of your input now? Now that this is your input current, basically, right?
Yeah, I see. It's the same as the voltage.
Correct. You got the
Okay.
answer.
So I
Just
was
a trick.
confused if it is same as output, then how are we defining the power factor if the frequency is different between the input voltage and output input current? Sorry, I got it.
Got it. Okay, good question. I guess we were here. Yeah, we completed this. Okay. Same question. The question where we left off just a few minutes back. A single phase voltage controller has input of 230 volt and a load of 50 ohm resistor. For 6 cycles on and 4 cycles off, determine the power delivered to the load. Again, this is a very easy question, I believe, because You obviously know what is your V naught, right? This is what we calculated. V naught is Vs into root over T on by T or root over N by N plus M, right? 6 by 6 plus 4. This is your V naught. Then what's your power? Power is simply V naught RMS square over R. Okay. So 178.157 square over R is 15 ohms. So what is the value that you get? So 178.157 divided by 15. So you should end up with 2.116 kilowatt, if I'm right. Yeah. So you will end up with 2.1 kilowatt. Simple, right? All of these are simple questions. Okay. Fine. Okay, so SMPS is used for dash obtaining controlled AC power supply, obtaining controlled DC power supply, storage of DC power, switch from one source to another. I don't want to linger on this question for longer. So the answer is to obtain a controlled DC power supply. Okay. In a three-phase half-wave cycloconverter, what takes place? Both inverting and converting action, only inversion, only conversion, or what? So again, just now we were seeing about cycloconverters. Cycloconverters, you can understand both inversion and conversion are happening, right? Over here, you see both inversion and conversion are going to happen. This is basically inversion period. Okay. And this is your conversion. Okay. So both inversion and conversion are happening. Okay. Over here, the question is for a three-phase half-wave cycloconverter. So this is the image of your three-phase half-wave cycloconverter. Obviously, we have a P converter and N converter, which will do conversion, I mean rectification and inversion respectively, right? So you're going to have both rectification and inversion. Okay, so both inverting and converting actions are going to take place. Okay. Okay. So this is a good, interesting question, I would tell. So the speed of a three-phase, two-pole 60 hertz synchronous motor is controlled by a step-down three-phase cycloconverter. Maximum speed of the motor is what? So you understand the question. So you have a synchronous motor, two-pole synchronous motor. Okay, 60 hertz. It is controlled by a step-down three-phase cycloconverter, right? So if you tell that it's a step-down three-phase cycloconverter, what is the meaning? It means that your output frequency is input frequency over 3. Correct? Step down three-phase cycloconverter. That means that your output frequency is basically 60 over 3. If your input is 60 hertz, then its output frequency is basically only 20 hertz, right? So this is your frequency of the cycloconverter. Now this cycloconverter is actually controlling the motor. Okay, so this cycloconverter is controlling your motor. So what is the synchronous speed? It's a synchronous motor, right? Therefore, you don't have any slip or stuff. Similar to your induction motors, you don't have slip, right? So what's your synchronous speed? NS in RPM is going to be 120 F over P, where P is the number of poles, right? So over here it is F naught over P. Why? It is being controlled by the cycloconverter. It's a three-phase step-down cycloconverter. I mean, yeah. So it's going to be 120 into 20 hertz divided by, it's a two-pole machine, right? So you're going to end up with 1200 RPM. Okay. Got it? You have a three-phase two-pole 60 hertz synchronous motor. It is controlled by the cycloconverter. So cycloconverter is stripping down the frequency by 3 times. Therefore, your synchronous speed is also down by 3. Okay, it's 1200. Okay. Okay. So cycloconverters used in AC motor speed control provide what frequency power from a what input voltage power, dash frequency power from a dash input frequency power. So what do? They provide variable frequency power from a fixed input frequency power. Correct? So you can make it variable and input is obviously fixed. Okay. Okay. So far, do you guys have any doubts, or else I would like to discuss a few more questions on inverters actually. So in this particular problem solving session, did you guys have any doubts from today's session? If you had any doubts, you can tell me. In the meantime, we'll just see one or two problems on inverters and then we will close for the day. Sorry, I forgot to unmute myself. Okay. So there's a question on Fourier series, okay, and it is applicable for inverters and of course for inverters. It's a question on single phase full bridge inverter. Okay. Okay. So the question is, so you have a single phase full bridge inverter. Okay. We have a single phase full bridge inverter, right? And it is being fed with a DC voltage of 230 volt. It is fed with a DC voltage of 230 volt. And the load values are R equal to 10 ohm and it has an L of 1 millihenry. Okay, so you have an R and an L as a load and L value is 1 millihenry. Okay. Right. So the question is quite interesting. Find the RMS value of third order harmonic current. Okay. And B is same for fifth order harmonic current. Okay, got the question. So you just have a full bridge inverter. DC voltage is given, R is given, L is given. Okay, find the RMS value of third order harmonic current and find the RMS value of the fifth order harmonic current. Okay, so how do we solve this? So basically, just put all your circuit theory knowledge aside. First, you try to understand the normal working of this inverter is something like you have a load over here and then you have the switches, correct? And the output you are going to get is obviously a square wave between plus VDC minus VDC and so on. Okay, it is plus VDC minus VDC. Okay, so what is the RMS value of this? So this can be written as, or this square wave can be written as V naught is basically sigma n equal to odd, right? 135 to infinity. 4 VDC by n pi sine n omega t. Correct? So this will be your V naught. Okay. So now how does your load current look like? See, you understood that your V naught is going to be something like this. Okay. So your load current would be looking something like, it may be an RC charging, right? So it will be something. Okay, and if I something like this, correct? So the idea is your IS, right? IS can be written as sigma n equal to odd to infinity 4 VDC by n pi whole divided by Z, right? Whole divided by the equivalent impedance. Okay, whole divided by the equivalent impedance, and then sine n omega t plus phi, correct? Where phi is your load angle. We have seen earlier itself. Phi is your load angle. Phi n is basically tan inverse of n omega L over R. N is the harmonic number. So basically, if you just have the amplitude of your square wave or the voltage and you divide it by the impedance, if you divide it by the impedance, then you will get the value. Here they have not asked anything to do with the angle, and also don't take unnecessary tension. The idea is just you need to have the amplitude of the square wave, that is 4 VDC by n pi, and then divided by Z, correct? So this will give the amplitude, correct? So what is your Z over here? Z is basically R plus J omega L, right? Into n, R plus J n omega L, where n is the harmonic number. Okay, so this is your Z, or we call it Zn. Okay, so if you just have 4 VDC by n pi, which is typical of the square wave, okay, and then you divide it by the impedance, equivalent impedance at that harmonic frequency, you will get the current. Okay, then this is the amplitude. Then if you divide by root 2, then you will get the RMS. Simple, right? 4 VDC by n pi divided by Zn, or your impedance, that is your current amplitude, correct? Then you divide it by root 2, you will get your RMS, correct? So this is the procedure we are going to follow, right? So for case 1, right? So what is your RMS voltage? Voltage RMS is 4 VDC by, it's your third harmonic, right? So they have asked for the third harmonic. So 4 VDC by 3 pi. Okay, 4 VDC by 3 pi is your amplitude. And what is the RMS value? By root 2. Okay, so how much do you get? Your VDC is basically given as 230 volt. So your VDC is 230 volt. How much do you get? You will be getting, you should be getting around 69 volts. Correct? So this is your RMS at the third harmonic. Okay. So now what will be the current? IRMS is going to be VRMS over Z, right? That is 69 divided by what is Z? Zn, right? That is R plus J into N omega L. Okay. That is over here it's a third harmonic. So R plus J into 3 omega L. Got it? That is 10 plus J into 3 times. If your frequency is, let's say, 50 hertz, then it is going to be 2 pi into 50 into L. L is 1 millihenry. Okay. So this is your Z. Okay. R plus J into N omega L. Please, guys, please solve these kind of problems. Okay. So in your competitive exams and all these kind of problems, if you solve over here, it will be really helpful. Okay, so it's going to be 3 into 2 into 3, 4, 3. So it's going to be 0.9. So 10 plus 0.94 J. 10 plus 0.94 J. So what is that in absolute terms? It is going to be 100 plus 100.8836. So if you take the root of that, you're again going to end up with 10. So it is almost going to be 10.04. And what's the angle? It's going to be 5.35. That's the angle. Okay, so this is your Zn. Got it? So substitute that back over here. So 69 divided by 10.04, angle 5.35. So the answer is around 6.84 minus 5.35 degrees. Got it? I just found out the VRMS just from Fourier series, then divided by Zn. Don't divide by Z. You should divide by Zn. Why? Because it is at that frequency, you need to see what is the equivalent impedance. Impedance changes with frequency, right? Basic stuff. So R plus Jn omega L. Okay, so N is your 3 and omega is 2 pi into 50. L is given as 1 millihenry. Okay, same way you can do it for fifth harmonic as well. Okay. So what is it? I will, if I might write directly, right? I phi RMS is basically V phi RMS over Z phi, correct? So V phi RMS is 4 VDC by N pi is phi, right? So 4 VDC by 5 pi divided by root 2. That is your RMS, correct? So what is the value 4 VDC by 5 pi divided by root 2? How much do you get? So you will get 41.41 volt. Okay. And then what is Z5? Z5 is R plus Jn omega L or phi omega L, correct? 10 plus J phi into 2 pi into 50 into 1 millihenry. Okay, so just compute this, you will get the answer. So you should get 0.9. 0.57, right? So 10 plus J 1.57 ohms. So what is that in absolute terms? You are going to get around 10.12 ohms. So just substitute over here 41.41 divided by 10.12. What is that? We will be getting you should get 4.09. Okay. Got this question? VRMS divided by Zn. Okay, use that always. Don't just use Z. That is also there. Okay, or else it's just Fourier series and basic network theory stuff, right? Okay, so at this point, I would like to end over here for today. If you have any doubts in today's class, in today's problems, whatever we saw today, please do go ahead and ask. I'll just pause for 2 minutes. And then or else we can conclude for the day. So this question, if you want, I hope you guys understood this question. It's a very important or interesting question, I will tell. If you have any doubts, please do go ahead and ask, or else we'll conclude for the day. Yeah, Divankar, just a second. I'll just read the chat. Input frequency is always fixed. I guess that is what we did, right? Output frequency changes, input frequency is fixed. Yeah, so cycloconverters provide variable frequency output power from a fixed input frequency, right? So I think that's what I have written as well. That is what we have tick marked, right? Variable frequency, input, fixed input frequency. Yeah. So okay, so if today's class was fine, then I guess we can conclude for the day. And just thank you guys for attending today's session and staying on till the end. I guess we saw a lot of important problems today. I hope they got benefited. We will meet again in the next week. So I'll just stop the recording. So yeah, take care and bye bye everyone. Have a great week ahead.